All right, welcome back. This topic that we'll be covering in the video today will be with regards to the design of members for shear. In particular, for most steel design problems in a normal setting, shear typically is not the controlling scenario for our design. More often than not, it is flexure or it's a serviceability criteria involving the moment of inertia for deflections or vibrations or something like that for most normal flexural members. However, if you get into very short spans with very high loads, sometimes these provisions will start to pop up. But 95% of the time, if not more, I find that when I'm designing a member for a structural application, the shear is not the controlling factor. Now we'll work through some examples just to show you what to do, but we'll take all of this kind of with a grain of salt since we're not sure what the scenario that you're going to be facing in practice is. Okay. Now that being said, for non-standard, non-compact shapes, the lambda problems or the LB problems that we faced when we were doing our flexural beam design in the last couple of videos, if you get into a scenario where neither one of those cases applies, you're into a realm of analysis called plate girders. And plate girders violate a lot of those height to thickness restrictions that you're going to see in this example. And when that happens, all bets are off, because more often than not, it is shear that will be the design and control for that. But for our scenario, we're going to focus only on the standard shapes, not the built up plate girders or sections like that. So anyway, as you can see, we're looking at the 15th edition AISC Manual of Steel Construction. Okay, the governing specifications are located in Chapter G. For once, the lettering kind of makes sense to me. I know most of the time you think, oh, shear, that's V, but G makes sense to me because if you remember back in mechanics and materials, the elastic shear modulus, the typical constant that's used for that value that relates the shear stress to the shear strain was the letter G. So that's one way that I can always remember this. It's not like some of those other scenarios that we looked at, like tension members that were located in, chapter D, or when we get to connections are often located in chapter J. Okay, it's kind of no rhyme or reason to the order, at least not that I've been made aware of. But I wanted to kind of show you some of the provisions. We'll kind of walk you through the specifications, and then we'll kind of go through some theory about what it is that shear is doing, and then lastly we'll work in a couple of design examples just to illustrate the procedure. Shear design or shear analysis is very straightforward. It's no major tricks, which is great news for us. All right, so all I want to show you now is I'm going to show you a couple of provisions. Okay, and in particular I want you to pay attention to the second one. Okay, for the I-shaped beams and channel. Trying to get the glare off of the page so you guys can see it okay. Okay, and that seems to be working all right. Okay, now you'll notice that like LRFD provisions, most of our general provisions are, let's see if I can put my hand so it doesn't autofocus on you. The phi factor for us for shear provisions will be 0.9 unless I meet the criteria of G2, in which case it changes. Right. So for the G2 that we have on there, and again I'll show you these in the notes, the rest of the provisions all kind of start to take place here. Okay, now you'll see that for our G2 scenario, if we meet a certain set of height to thickness ratio requirements, they're going to change the phi value to 1.0. Okay, but there's also another constant that kind of sneaks in, and that's this CV guy, and we'll kind of start to explain this as well, and as well as some shortcuts. Okay, and then there's some other criteria that we'll start to get into. It's the rest of the section after this first page where we start to get into trouble. Okay, and these are the plate girder provisions that will show up something kind of like this, and predominantly it has to do with the size dimensions of the panel. Okay, which means it's basically the distance between vertical stiffeners, because one way that you can build or increase your shear capacity if it becomes a problem is you can stabilize the web by welding vertical plate stiffeners. Now if you've ever been traveling down the highway and gone under a bridge trestle or something, you see these big deep built up sections, these big plate girders, and every so often there's a vertical member that kind comes in, and what they're doing is they're stiffening the web. So that's, they're called stiffeners, transverse stiffeners or web stiffeners or something like that. And it's the spacing between those versus the depth is the controlling characteristic. And so you'll see this idea of this web panel or this A to H ratio. Again, that's beyond the scope of what we're doing here, but if you get into an advanced steel design class or something you might see in graduate school, if you go there, they'll talk a lot more about this, and they'll start to describe this phenomenon called tension field action. Okay, but again, for us, we're not going to deal with that. So anyway, like I say, it's very simple. It pretty much boils down to just this one page. Okay, let me pull this thing back up a little bit. Okay, and then we'll get on to the actual lessons that we're going to deal with. All right, so let's pull. And turn that down a little bit. See if I can zoom in a click or two here. Okay, all right, so the basic relationship that happens with shear, it goes back to mechanics and materials, okay, and just like we did with tension members, where we had stress, that the tension load was some stress multiplied by a relative area. Shear is the exact same way. So what this is not, if you remember mechanics and materials, we always had the relationship that tau was equal to VQ over IT, okay? And what that did is that produced, for a rectangular section, some sort of shear stress distribution that looked something kind of like this, okay? In which the tau max was that guy right there in the middle, okay? And we've talked about this in some of our other classes and some of our other lectures, okay? Where you had a tau of 0 at the top, a tau of 0 at the bottom, but this tau max always kind of lived here at this location, kind of at the neutral axis, okay? That's the real mechanics approximation. AISC doesn't make you do this because if you remember, Q was always kind of tricky to calculate. I is what I is, and T is the width of the section that you're looking at. But Q was always this first moment of area in a section property. Not hard, but just kind of a little bit cumbersome to be able to do that. So what AISC does, like they do in so many of their other cases, is they choose to go with an allowable stress. Okay, and so what they do is they take the tau yielding, which is the shear yield stress, okay, multiplied by the area of the web, okay, and so again, for an I-beam, if you look at this, and we'll talk a little bit more about this, if this is my awesome graphics live on demand, right? Okay, that's our I-beam. This area of web is only the region here. Okay, that's AW. Okay, it ignores the flanges. Okay, and that should make sense because out at the end regions, remember at the top tau is 0, and at the bottom tau is 0, and its tau max is located in the middle here at the web location for a doubly symmetric shape. All right, so really you're getting very little resistance in these little bitty regions that are kind of happening up toward the end. So most of the strength is in the web of the beam. So AISC just says, hey, just discount the webs, and this calculation becomes very, very simple, especially for the standard shapes. Okay, all right, so what we do is we assume, now notice that they're using tau y, okay, which is the shear yield stress, okay? Remember, Fy in all of the beam design that we've done up to this point, our section properties, Fy and Fu were all based off of tensile coupon test, right? And we talked about that, where I deal with this and then I plot stresses versus strain. Okay, and then Fy is the point where this thing first yields, and Fu is the highest value that's achieved, and then you've got a rupture value when this thing actually breaks. Okay, well, studies show that the approximate relationship between a beam that's failed due to a normal stress, which is what those Fy and Fu values are based off of, okay, that the shear capacity, again, for shear, a shear failure would look something like this, where I put a load here, I would put a load here, and then we'd look at failing it along that axis, okay? So it's a little bit of a different animal, okay, as that goes, okay? So our constants are made off of a normal test. This is a sigma, okay? This guy is a tau, okay, in which you're actually trying to shear the thing or trying to break this thing. Imagine it's like a piece of chalk or a wooden pencil or something, and you're trying to snap this thing by moving your hands relative, parallel to each other, as opposed to trying to make it longer, okay? That's the difference between normal and shear stress. Okay, and so this tau y, they found that they're, instead of making us go do this test every time, they found that there's a correlation of this guy being 0.6 times Fy. In fact, AISC and a lot of sources recommend that it's more like 0.59, but for what we're doing, that's close enough. Again, we're doing some rounding and doing a little bit of crude math just to simplify the process, because we are underestimating the capacity because we've neglected the flanges, and that will bias back the little bit that we need to do. All right, so that's our tau y. Okay, our area of web, like we talked about, is then going to be the depth of the beam, which is from top to bottom, which that's a tabulated value for the standard shapes. And TW is the web thickness. That's this dimension here. Okay, so it's all terms that you guys know and are capable of working with. Okay, so that's the basic mechanics approach. Okay, and so when you plug all those pieces in, you come up with a formula that looks something kind of like that. Okay, and so the nominal shear capacity, and this is in that section G of the manual, is 0.6 times Fy. That's your tau. Okay, this is tau. That's your tau y, okay, and then multiplied by the area of the web, and then multiplied by this last little constant, this CV characteristic. And what this is kind of a shape characteristic. And so there is a little bit of, if you're doing a round pipe, or if you're doing a plate girder, or if you're doing an I-beam, this value can change a little bit. So this is kind of the magic multiplier that AISC adds in that isn't in the theoretical computation for what we have happening here. All right, now, it's very, very easy, okay? And so in particular, I'm going to point you to that provision I showed you in the code, which was the G2.1a, okay? Just because the glare on the page is kind of inconvenient, I want to show you from here, right? Okay, now, the parameter that matters, okay, for shear design is basically a height to width ratio. It's a width to thickness ratio. Now you guys have seen these parameters before back when we were doing flexure and checking compactness. Right? H over TW is one of the ones that you checked in the lambda criterion. Okay, for the web anyway. And so just like you did before there, you have to figure out what region that you're in. And so the AISC code says that we're going to compare this H over TW value for the shape that we choose, and is it less than 2.24 times that square root of E over Fy? So this is no different than what we did for the flexural calculation, right? It's that E over Fy quantity. Again, E is Young's modulus, Fy is the yield strength, the normal yield strength, not the tensile. We're not worried about the 0.6 on this guy, okay? And then it's just basically a characteristic of this. If this value of the beam that you've selected is less than this quantity, okay, then this is that case 2.1a, right? And so CV is 1.0 and phi is 1.0 for this, okay? This covers the vast majority of standard sections if our Fy is equal to 50 KSI. Okay, now I will point out to you, for the few cases where there is an exception, and I'll show you one of these, just like with flexure, like in the W8/31, when they put an F to indicate that it was into that second region, it wasn't at the plastic moment capacity for the nominal moment, okay? They indicate with a little letter V as a superscript that you've got a problem. And for I-beams, if it has a V superscript, you violate this. Okay, in which case, then it puts us down into the other case, all right? So if we meet this criteria, it's 1.0 and 1.0 for CV and phi. Okay, otherwise, for all other cases in the I-beam family, okay, except for, the HSS round shapes on there, phi is equal to 0.9. Okay, so that's the one check. Okay, so we've got a little bit, we're getting into a little bit of instability. Okay, and so we're putting a little bit of extra safety on this particular scenario. So we're going from 1.0 down to 0.9. Okay, now the other check that you have to do, if I don't meet that criteria, then is I got to check that H over TW, because again, they're trying to standardize these formulas so that it's not just the height to depth ratio of of just I-beams or S-shapes or whatever the case. They're trying to standardize this for, just even single plates, which is needed in, the construction of plate girders and those kind of approaches. Okay, they're going to do another check then if you're down in this other case where we violated this one. Are we less than 1.10? And then there's this KVE over Fy. If we are, then CV is 1.0. Now the pieces of the puzzle for this, okay, this indicates that there's no instability in the web. We're not getting into that tension field action or anything like that. Okay. All right, so you may have noticed that there was a minor pause there and that some of the information at the bottom of this page has changed. Apparently, I can't do simple math, so I needed to make a correction. So if you notice that the numbers on these last two lines have been altered a little bit, this is the reason why. So anyway, as we were saying, if our H over TW ratio is less than that 1.10 times the square root of KVE Fy, the CV is 1.0, that means that there was no instability, and that the K factor, that KV value, that's showing up in the upper part of this equation is equal to 5.0 for all cases where h over tw is less than 260. All right, so if we do kind of as a quick example to illustrate why this isn't a concern for most standard shapes, if I went on the high end and assumed that the web thickness is a 1/2 inch, and again, that's a pretty high value for some of the deeper sections. Then if I run this formula backwards and solve for the corresponding h that would fail this criteria, our h max would be 130 inches, okay, which is right around 11 feet, like 10.9 feet deep. All right, so most standard shapes do not get anywhere near 11 foot in depth. Okay. I think the largest W section I think is a 44 incher or something. I mean, they're big, but they're nowhere near this limit. All right, that's why it's only a few cases, a handful, like 6 or 7 of them, that will violate, that will have these shear problems start to creep in that we have to kind of consider otherwise. Okay, so for all practical purposes, when you're looking at a W shape or these doubly symmetric shapes, whether it's a W or an S or an H section, or even the channels for that matter, KV is always 5.0. Okay, it's only the plate girders that are going to get you in trouble where we have to start doing something a little bit different. All right, so with that being said, I now return you to your regularly scheduled program. Back to it. All right, so if we were to take a look at kind of the overall shear behavior of this beam, and if I were to plot my CV value versus this H over TW, you get a curve that looks a lot like the curves that we've seen when we were studying the compactness criteria, or we were studying the columns versus their nominal capacities for those kind of things. And so basically what happens is the whole definition of CV gets broken out into 3 regions. I get a region 1, okay, a region 2, and a region 3, okay. Now these region numbers aren't official AISC designators, it's just what I use to refer to the different regions of the graph myself. This kind of helps me kind of define things. So region 1 is defined as no instability. Region 2 is where we're getting into inelastic buckling in shear, which is where the web is starting to buckle. And then region 3 would be an elastic buckling, which is a much weaker limit state. And so you can kind of see some of the relationships. And like I say, we won't spend a lot of time on this. These are in the manual. But it basically boils down to that for region 1, the CV value ends up being 1.0, okay? And so this divider line, this limit, if you will, is that 1.10 times the square root of KVE over FY, okay? This is where there's no web instability happening there. And again, this is a very large number starts to come into play on these particular ratios. Okay, and so that becomes the divider point there. And then if you go into the elastic buckling separator, that would be this 1.37 times the square root of KVE over Fy. Okay, and so these last 2 regions, and particularly region 3, well, region 2 for that matter, if I had just a simple beam, if I slide this over a little bit and look at you, maybe I have a simply supported beam, and here's my cross section, and I have some sort of applied load that causes a constant shear across the web. This may be some sort of W-shaped cross section. Okay, if I start getting into problems and I find myself creeping down into one of these other 2 regions, which often is the case with the plate girder problem, if I'm down in one of these 2 regions, what I can do to move myself back up into one of the more stable regions is I can start to add these transverse stiffeners or these web stiffeners in here. So a lot of times, W shapes don't need them because the loads aren't big enough, but every once in a while you'll see a W shape with, a web stiffener that's been welded in, generally near a support reaction or near where a point load is coming in, okay, and shear may be one of the reasons for that. Now it could also be a case where, I have a concentrated load and, I'm trying to get the load spread out into the beam without failing it locally, but that's another concern for, when we get into bearing, bearing criteria. But but that's one of the tricks that you can do, and that's why shear isn't a big issue. If we have a problem, it's generally pretty easily correctable for us to be able to go through and do that. Okay, all right. So look there. All right. So let's run through an example fairly quickly, kind of show you how we're going to do it. Okay, for us, now again, normally you don't just say I'm going to design this beam for shear. Okay, so what we're going to do instead is we're going to look at coming in and doing some basic calculations. So what we have is we have a simply supported beam, okay, And if you notice the loads on this particular example, okay, they are very unusual. I have a dead load of 1 kip per foot, and that's not unusual, but this live load is now 20 kips per foot, or sorry, 19 kips per foot. That's a massive, massive number. If you see something like that on a very short span, in this case, this beam is 5 feet, I mean, if you do the math on this without factoring the loads, 5 times 19 plus 1 is 100 kips. You're putting 100 kips of load onto a beam that's very, very short, all right? And that's bad news for shear, for the design of shear. Okay, now what we're gonna do is we're gonna try to choose a section for both flexure and shear since they go together, and I'll show you how we start to kind of go through the process. Now again, normally we design for flexure first, and so we'll do that real quick on this. Okay, first step, we're going to factor the load. So this is your typical 1.2 dead plus 1.6 live. So 1.2 times 1 plus 1.6 times 19, that's 32 kips per foot. That's a massive, massive load. Okay, and again, this is kind of just an example to kind of illustrate the procedure more than anything. All right, so we can go through, we can draw our shear moment diagrams. Okay, so we're simply supported there. Okay, and so we know that our shear capacity that's here is going to be WL over 2. So we're going to take 32 times 5 feet divided by 2. We have an 80 kip value of shear right there. And so that's about, whenever I'm doing a design on a beam, if I start seeing 40, 50 kips on something, that's when my ears start to perk up and go, we might be getting into a range where shear starts becoming a consideration. Now, if you're a lot less than that, then shear seldom is. Now, as an engineer, we have to do our due diligence and do the checks, but again, if we're just kind of looking for rules of thumb or when I might be concerned, this is one of the cases that would put a red flag for me and say, we might need to take a look at this a little closer or come up with another alternative or whatever the case may be. All right, now, so the moment diagram, you know, then is parabolic. That's the old WL squared over 8 because this was uniformly loaded over the entire length. So 32 times 5 squared divided by 8. We're looking at 100 foot kips, okay? So, I mean, that's not an insignificant moment, but it's not huge. Okay, let's start to kind of look at that. Okay, so first thing that we're going to do, we're going to assume that we're going to choose a compact shape, which again, unless it's denoted with an F in the AISC manuals, okay, all standard shapes are compact. For the ones that are just the standard tabulated values up in the first section of the book. Okay, so if that's the case, we're going to assume that it's compact, which means then that lambda is less than lambda p, so we're going to look at the nominal moment capacity as the plastic moment, and so then this becomes a relationship. Our nominal moment with phi on it is the same as phi with mp, and we know that mp is the x times fy. So that's all we're going to do, and we recall for bending phi is 0.9. Okay, so we're doing a 36 KSI beam on this, so we can quickly solve for a ZX required. And that's by taking the moment. Now watch your units. Again, you've got to convert. This was in kip feet, so I need to do multiply by 12, which is inches per foot, and this is in KSI to get my units to line up. And when I do the math, it says that I need a ZX of 37.0 inches cubed. All right, now we can go into the flexural tables, and we can pull out, you know, the first one that meets this criterion. So W12 by 26 looks like a promising candidate. ZX is 37.2. Okay, and now once I have this shape, now I'm going to pull the H over TW value of 47.2, and then the depth, of course, is 12.2, and TW is 0.23 inches for that. Okay, so nothing surprising here. This is just all we've done with the flexure. Okay, now, like I said, we kind of hinted that we might have a problem with our shear capacity. Okay, so all we're going to do is we're going to calculate, we're going to check our shear, and I'm going to check it against that limit. So H over TW is 47.2. That's the value of our shape. Okay, are we less than 2.24 square root of E over Fy? That's all there is to it. Okay, so I'm going to take 29,000, I'm going to divide by 36. Again, watch the units. This has to be KSI, that has to be KSI. Okay, and so we get a value of 63.6. Okay, and so my 47.2 is less than 63.6. There's no instability. We're over in that first region on the graph. So that tells me that CV is 1.0 and PV is 1.0. So this is a stable section. Okay, and this will be, like I say, the vast majority of times in standard I-beams, that's the criteria that will happen. So once I do that, then I can go in and I can calculate my nominal shear capacity, and that's 1.0 times 0.6 times Fy times D times TW. And if I plug all that in, you'll see that the capacity of that beam is 60.7 kips. And that's less than the 80 I need, so therefore we're no good. Okay, so that's a problem. So the beam was good for flexure, but it wasn't good for shear based on the capacity. I mean, that's a pretty substantial shear load. It's just that we were so heavily loaded that that became a problem. All right, so this is how we start to kind of resolve that issue, okay? And what happens is that when shear controls, you know, and we knew it controlled because it wasn't good here, but it was good for flexure up at the top. Okay, typically the way that you increase the shear capacity, it's a lot more economical to increase the depth of the beam versus making it thicker. Okay, because you're also getting a lot of added benefits by increasing the depth. We're increasing the eye, we're, you know, helping with the deflection criteria, all sorts of things that work like that. So all we're going to do is we're going to take this formula. Okay, so again, remember that this was AW, okay, and I'm going to rearrange this a little bit, okay, and so instead I'm going to, you know, all of this stuff will stay the same. I know that this is 80 kips, okay, I'm going to solve for what my required area of web would need to be, okay, and if we do that, that's going to be my 80 kips over my 1.0 phi over 0.6 over 36 KSI. The area of the web that's required is 3.73 inches squared. Okay, now again, we didn't specify what depth we were going to go to or what a thickness needed to be, so we just start playing some values, and we were at 12, it didn't work, so let's go to the next standard size and look at a 14. And so if I choose a 14 around 14 inches, I need a web thickness that's 0.26 inches. It's slightly larger than 1/4 of an inch. Okay, and so the first one that meets that set of criteria is a W14 by 34. It has a web thickness of 5/16 of an inch, that's 0.3125. And then we have a ZX value of 54.6 inches cubed. Now I'm writing both of these because, again, this ZX, we're still being bound by comparing to that ZX of 37 up here at the top. So we want to make sure that we're still above that when we choose our new shape for our next go around. Okay. All right. And then just for comparison's sake, if I go to D and I choose a 16 incher, the web thickness is 0.233. Now we're under that 1/4 inch. That's kind of a magic milestone, if you will, right? A 1/4 inch is a pretty, you know, if we can get under that, then we might get some significant savings, because that bumped us from 5/16 to 1/4 here. Okay, and so to make this one work, I can get away with a 16 by 26. Okay, as my particular beam shape. Okay, and so TW is 1 1/4 of an inch, and then ZX is 44.2 inches cubed. All right, so we're going to try our W16 by 26 because clearly it's lighter, so it's more economical. All right, so again, all we have to do now is just run back through our checks for shear. We're going to check H over TW. Its value is 56.8. This side, the 63.6 number never changed. So with that, we should be okay. Okay. Now again, what might happen in this particular scenario is that you might find that I can make a lighter shape work for us. It might need to do some sort of stiffener design, but more than likely we won't. And if that's the case, you may get stepped up, again, even based off of the stiffeners. But again, that's beyond the scope of what we're looking. That's all that we're looking for. So if we choose a W16 by 26 by 5 foot in length, okay, we're looking at a member that is, you know, just running a quick $1.50 per pound, 26 pounds per foot times 5 feet. This member is about $200 to give you kind of the sense of the scale of the pricing that we have happening on that. Otherwise, that's really all there is to it for shear. It's pretty straightforward. It's kind of an after check. The only thing you got to remember is we got to check the criteria. Now let me show you one last thing here, and I'll show you that indicator that we were looking for. If I go and I look at this little situated here. All right, so if I look at my shapes, can I zoom this in just a little bit for you guys? And it's a little hard, but I'm going to kind of down on the lower end of this table. The first attempt that we had was that W12 by 26 guy. And you can see, and like I say, I apologize, it's not real clear. Can I get it to focus a little bit? Not really. Okay, like I say, we're looking at page 1-26 on this, but it's these little superscript values are the ones that kind of give you the tip off, okay? And so just so you can see one that you can look at, and like I said, there aren't many of them in this book, and they're usually down at the bottom sizes of a shape. If you look at a W12 by 14, it has a C superscript, but it also has a V superscript. All right, and when I do this, this tells me that I violated that first principle, that G2.1a principle, as we start to look on that. All right, but so that's what you're looking for, is that little V that's hanging out there. So it basically says that the shape does not meet the H over T limit for shear in AISC specification, section G2.1a with an FY of 50 KSI. So again, for 50 KSI, they've superscripted and saved you a lot of the checks on that. Okay, that we know what my CV and what my PV values will have to be, just based off of whether it has that superscript or not, if I'm dealing with 50 KSI. So anyway, that's all we've got for that. Stay tuned and we'll keep on moving on. All right. If you got any questions or anything, leave me a comment down below, or you can email me at home, those of you that are my students, and I'll be happy to talk a little bit. But I hope this has kind of illustrated the shear design provisions that AISC uses. Thank you much. I'll talk to y'all later. Bye.